Okay, so this is the last lecture of the unit. A couple loose ends to tie up, and then we're going to talk about polyprotic salts and how they hydrolyze. So nothing big and new today. It's just building on what we did yesterday. One thing I do want to look at really quick, if you flip through, I know it looks like we're skipping a lot of pages in the notes. A lot of those you're going to need to go back and read over after the lectures. I think they'll make more sense than me just sitting here reading them to you, so be sure to go back. But what I want to look at is kind of the concept of why are acids acids and why are bases bases. If you ever thought about sodium hydroxide, we just like talk about, oh, it ionizes and OH comes off, but we really never said why. Why can't it split at the H and be an acid? And so the reason that is, and this is an example of why, has to do mainly with the fact that sodium hydroxide has such a low electronegativity. It's giving away electrons like crazy. So it is more apt to give away its electron, causing the break here, than hydrogen, which has a pretty high electronegativity, does. Hydrogen is like going to hang on to that oxygen for dear life. So the break will occur here. And that's why sodium hydroxide is a base. Versus this guy, why can't this split and be a base? Well, this has to do with little poor O in the middle of a tug-of-war. This little O is getting tugged on by a fairly reasonably electronegative H, but this S and all its buddies have a very, very strong dipole moment. And so the overall dipole moment in this direction is strong enough to where this oxygen, who is going left and right, which way do I go, which way do I go? Do I go with the S, do I go with the O? It's going to say, fine, release its electron and let H take off, and it itself is going to stay with his gang on the left side. Okay? So that's just a very simplistic view of why we have splits where we split. Okay? Another thing I want to look at before we go on is the strengths of acids. We're going to look at this first box and number 1. You can actually just cross number 2 out. This gets confusing, so we're not even going to worry about that. But what I really want to look at with number 1, we've talked about the acids. We've talked about HI, HBr, and HCl being strong acids, while something like HF is weak. Why would HF be really weak versus something like HI, which would be strong? What happens as you go toward F? Electronegativity increases significantly. So F being super, super, super duper electronegative is going to hold on to that H like crazy. If it's holding on to the H, is it dissociating? No, so that's a weak acid. HI, which is huge, not quite as high as electronegativity, is more apt to release the H and dissociate. Okay, and so that's the trend. As you go up the chart, this is up the chart. As you go up the chart, it gets weaker and weaker and weaker and weaker. The acids do. The binary acids. Make sense? Okay. And the other thing I want to look at, remember the rule that we told you in determining strong and weak acids was if there's 2 or more O's than H's, it's strong. So the more O's you have, the stronger it gets. Why is that? Well, it has to do with the structure of these. And I'm being really sloppy with electrons in these pictures. You have that versus HCl, OO, and then here we have HCl, OOO. The more O's you have, the stronger the electrons, or the more the electrons are attracted toward this side of the molecule, so the stronger the dipole. Therefore, this is going to release this one electron easier. It's like, I'm going this way. The chlorine's like, I'm going here, CH. Here, not quite as much of a pull, so this is going to be holding on a little bit tighter, making this the weaker acid. Here, man, this chlorine's like, I'm out of here. Bye to the H. And you get the highest dissociation. So the more oxygens you have, the more the electronegativity of the molecule, the more the dipole moment causing that to happen. Okay? So those are the loose ends I was talking about. Now we can actually get into the crux of today. First thing we're going to do is talk about these multiple H's on acids. Everyone take a look at, turn one page over, and you're going to see charts. Everyone look at those charts. In the middle of the page, and I guess I should pull them up here so people can see them. In the middle of the page, you have a chart for these acids that are polyprotics. So there's carbonic acid. If you look, carbonic acid has 1, 2 Ks. What do those Ks represent? They represent the dissociation of one K of H and then the dissociation of the other H. So we're today going to look at both carbonic and phosphoric, and we'll talk about how the dissociations affect pH. So I don't know if you remember at the very beginning of the unit, I had mentioned that when you're looking at dissociation of multiple H's, you only count the first one. Do y'all remember me saying that? I'm going to prove to you mathematically why that is today. So first thing it says, write 2 dissociation reactions showing diprotic behavior. So we're going to do that. When this dissociates, it is weak because it's a weak acid. We lose 1 H. What do we make? HCO3 minus and H plus. Okay? This is represented by that Ka1 on the table. Okay? And then we're going to dissociate a second time. And again, that's also weak. And we're going to make CO3 minus 2 plus H plus, and that is our Ka2. I'm going to prove to you that when you're finding the pH, this H is the only H we look at to do the calculation. This H down here is mathematically negligible. So we don't count it. Only count the first dissociation towards pH. Why? And we're going to show that. All right, so we're going to start with a rice table. You already know how to do this. And we're going to use the rice table for the first dissociation because that's what the problem says. It says, in your calculation, assume only the first dissociation occurs. So we're going to take our H2CO3, dissociate it, and we get H plus HCO3 minus. Our initial concentration of this guy is 0.1, 0, 0. Got to shift to the right, minus X, plus X. Now normally I would trump, but I'm not going to for this problem because I want the math to be very clear. I don't want any cheating. I want you to see how it actually works out. So to solve, we're going to set this equal to x squared over 0.1 minus x. We're going to set that equal to the K, 4.3 times 10 to the negative 7. So the H plus concentration, which is what we're looking for, is equal to X. I have all this worked out, so I'm just going to write down. When I cross multiply, and I know that Tess and her fancy calculator is going to have this done before I even can find it on my page. All right, when I cross multiply, here I get x squared is equal to 4.3 times 10 to the negative 8th minus 4.3 times 10 to the negative 7th x. And then combining like terms, well, I'm just plug this in. You can just plug it into quad form and make this one negative and make that one positive. And this is A, that's B, and that's C. And when you do, okay, yeah, 2.07 times 10 to the negative 4th moles per liter. And that's equal to the H plus concentration. I had the last class just for grins. I want to know what the pH is for that value, and it came out negative log of that. You get a pH of 3.68. So that's just from the first dissociation. The question is, okay, well, the second one happens right away. So what does the addition of that H do to this concentration? Does it increase it enough to make a difference? All right, so let's go to that next dissociation. Here's the important part about that second dissociation. It happens after the first dissociation. So the products of our first dissociation, or that equilibrium concentrations, those become the initial concentrations of our next dissociation because one happens right after the other. So when we do our Rice table, we don't put 0 for those initial concentrations. We actually put the previous concentrations from the first dissociation. So we're going to do the second dissociation. We have HCO3 minus plus H2O. Oh, I'm not going to do the plus H2O. I did that earlier. I'm just dissociating it here. And we are going to get H plus CO3 minus 2. When we started the second dissociation, remember we finished with some of the HCO3 as a product of the other one. How much was that? It was X, correct, 2.07 times 10 to the negative 4th. We also had 2.07 times 10 to the negative 4th of this H plus. Carbonate, we didn't have any of that yet. That hadn't been made. We still have to shift right, though, because we got to shift to the 0. So we end up with 2.07 E negative 4. I can't believe I just wrote E minus X. I think it must be Friday. The epitome of laziness. Plus X and X. All right. So to solve for this, again, ugly math, we're going to set the K. This time it's K2. How does K2 different than K1? It's smaller, meaning it's less apt to dissociate. We're leaning more toward the reactants on these reactions, and that's what happens. Every time you dissociate, the K gets smaller and smaller and smaller. So 5.6 times 10 to the negative 11 equals 2.07 times 10 to the negative 4th. And I'm just going to cross multiply. I'm not distribute right now. X plus X squared all over. That's products over reactants, 2.07 times 10 to the negative 4th minus X. So when I cross multiply, ugly math, I end up with 1.16 times 10 to the negative 14th minus 5.6 times 10 to the negative 11th X. That's going to be equal to, I'm going to run out of room, 2.07 E negative 4 plus X squared. Combining like terms, I get 0 equal to X squared plus 2.07 times 10 to the negative 4th X minus 1.16 times 10 to the negative 14th. Plugging that into quad form. I'm worried about this one. I don't believe them. So why don't you all tell me? Yep, that's what they got. 5.6 times 10 to the negative 11th. Okay, that's our X. We need to find this H concentration to see how it's affected. So, add 2.07 E negative 4 to that. Are y'all really putting it in your calculator? Silly gooses. Oh, did you? Yeah, do you see how when you add it, if you're rounding, I'm sure like Tessa's calculator is going to tell us something different. Oh, okay. I feel like have we had this conversation before? Or did I dream it? That's weird. I'm experiencing incredible deja vu right now. That's really weird. I feel like she was like, but in my deja vu, you actually found a difference. But anyway, the point is when you add that to the 11th to that, you're going to get the same concentration so therefore your pH is the same. So someone actually didn't have it on approximate mode earlier, and they figured out it changed the pH on the 7th decimal by like 3 units on the 7th decimal place. Yeah. The problem is I like challenge anyone to find any sort of instrument anywhere that measures pH out that accurately. Good luck. So anyway, so what the point of this is you really only need to worry about the dissociation of the 1H. Where I get concerned, and this is mainly because y'all are going to have to just bear with me here. This is for mainly all the teachers that are listening to this video. I want to make sure. I see this all the time when I travel. I see teachers doing the following. I see teachers, if I give them a problem that says, if I have a 0.713 molar sulfuric acid, and I tell them to find the pH, the real way to do it is to do what? You just take the negative log of 0.713. Can someone calculate that? I just pulled that out of my head. So the negative log of 0.713 is 0.147. So that's the pH. That's the correct answer. But here's what I see teachers teaching, and I see them doing with their kids. They say, oh, well, it's not 0.713. That's not the true concentration of the H+. They say, oh, it's strong. So you make this plus this. And when you do that, this might be 0.713. They say, well, stoichiometrically, you have, what's this, 1.42 moles per liter. And so they'll take the negative log of 1.2 moles per liter. It's wrong. Why is that a wrong assumption? Anyone know? Well, we dissociate one at a time. So let's look at that. If we dissociate the first one, the first dissociation, yes, it is a strong dissociation, and you get this. But when you dissociate this, this puppy is no longer a strong acid. He does not dissociate 100%. He's doing that, and he makes this plus that. And he has a K that's super small. So when you have to do the same thing, you have to negative log of it, and then, which is what we did here, and then do a rice table. And if we did, we'd come up with the same situation where the H+ concentration wouldn't change enough to change this pH value. So that's the point. Do not mess with multiple H's. Only the first one. All right? All right. Last bit we have to cover is hydrolysis. And we kind of already did this yesterday, but this is hydrolysis with a twist. So how do I know this is a hydrolysis or a salt solution problem? That's a salt, right? That's not an acid, that's not a base, it's an ionic compound. Okay? So what was the first step in doing this? Find the weak part of the salt, which is what? H2PO4 what? Plus? Did I hear plus? I just had a heart attack because you said plus. Minus. Minus. Okay. The sodium ion comes from that sodium hydroxide. That's not going to undergo hydrolysis. This will. But here's the twist. Let's see if y'all, does anyone recognize the issue that we have here? It's polyprotic, yeah, but what does that mean for us right here? Okay, we can take away, make HPO4 minus 2, but what else can we do? It can add. Do you see how this can either gain and make H3PO4 or lose and make H2PO4 minus 1? You see that? Okay. HPO4, excuse me, HPO4 minus 2. When I do this many hours in a row, you're lucky I'm even still talking. So we're going to write both equations and talk about which one is the right one. Which one do we put in the rice table to start the problem? So let's go ahead and make acidic first. We'll do H3O plus. So we're left with what? HPO4 minus 2. Okay, so now let's write the other one the other direction. And this time the water is going to donate and be the acid, leaving us with OH minus plus H3PO4. Oh boy, Which one is it? Well, this is where you need to utilize that table. So if everyone goes to the next table, and you can actually even write this on the page. I'm going to write a series of dissociation equations along with the K's to help you with these problems. On your test, I suggest you do what I'm about to show you, like in the top corner somewhere, and use it as a reference for this problem. Otherwise, your eyes are going to cross and you're going to get really confused. So if you look at phosphoric acid, and it's 3 Ks on the next page, let's write a description as to what's going on with these. H3PO4, when it first dissociates, makes H plus HPO. Make sure my chargers are good again. When it gets late, I get crazy. And then if you can't read it, the K1 for this is 7.5 times 10 to the negative 3. That's the K1. All right. Now, the K2, all I'm doing is dissociating phosphoric acid 3 times. When I do this, I messed up. You guys need to watch me. Watch me. So that's my charges are good, and I get HPO4 minus 2 plus H plus. And that's my K2, which it's hard to read. It's 6.2 E negative 8. And my last dissociation equation, HPO4 minus 2, gives me PO4 minus 3 plus H plus. So my K3 then is equal to 4.8 times 10 to the negative 13. So the reason I'm doing this is just for reference to solve this problem. Okay, so I wrote my 3 dissociation equations and wrote the K's next to them from the table. All right, so looking at the first equation up here, I'm going to, basically the goal is to find K's for both of these and compare them. This one is an actual K, it's listed. Do you see how it's making an acid? Which K is this representing? Look down at the equations we just wrote. It's the second one, right? So there's our K2. The K for this reaction then is 6.2 times 10 to the negative 8. That one was easy. But look at this one. Do you see how it's a KB? All right? So we need to find the KB of that equation, but notice we kind of know the Ka of the conjugate, right? Look down below. Which one is that kind of the reverse of? Not exactly reverse because it's got OH in it, but isn't this the same conjugate pair as above? So this is the Ka we're going to use and convert from Ka to Kb, and it's going to be K1. So Kw, let me just actually write the value for Kw. 1 times 10 to the negative 14th divided by 7.5 times 10 to the negative 3rd comes out to be 1.3 negative what? Negative 12. So there's the 2 Ks that represent those reactions. Which one of those is more apt to dissociate? Which is a better dissociation, the first one or the second? The first one. Why? It's a bigger K. So this is the reaction we're going to use in our rice table. All right, so now I'm going to write really small in black since I've used up the majority of the screen. Hope I can fit it. And now we solve like you learned yesterday. So we have the equation up. The one we chose was the bigger K, H2PO4 minus 1 plus H2O makes H3O plus. So this is a review from yesterday. Nothing new about this. And then we have our initial concentration. They gave us in the problem is 0.1. No water, 0, 0, minus X, plus X, plus X. I'm going to trump it for sure. I didn't trump that last problem because for demonstration purposes, but we're trumping this one. So we're going to set up our X squared over 0.1 equal to the K 6.2 times 10 to the negative 8. That's going to give me my H plus concentration. Y'all get 7.9 E negative 5. And then that's moles per liter. So if we take the negative log of that, we get a pH of 4.10. All right, so let's do another. We're going to find this salt solution. We're going to take the weak part of the salt, and we're going to have HPO4 minus 2 plus water, because that's the weak portion. And we're going to go, uh-oh, that's one of those ones that I can send H's either direction. So I always like to make my acidic one first, just because I know I have Kas, so I don't have to do funky stuff with it. So I end up with PO4 minus 3 plus H3O plus. And then in the basic one, I have HPO4 minus 2. This time, the H is going to go from the water to the biphosphate, and we get H2PO4 negative 1 plus H3O plus. Okay, so we're going to figure out which is a better possibility by looking at the Ks. The first reaction is acidic. And I messed up because we're not making H3O plus, we're making OH. All right, so looking at the first equation, that's our acidic one, so we should find it as is. Which K is that? That's K3, so K3, 4.8 times 10 to the negative 13. Now let's go ahead and find the other one. Well, I know I need a KB. So KB is equal to 1 times 10 to the negative 14th, which is this, K1. If we think about this going reverse, that's K2. So it is a K2, is 6.2 E negative 8, giving me an overall KB of 1.6 times 10 to the negative 7th. All right, so I'm going to stop the video. I'm encouraging people at home to stop the video, work this problem, and when you turn it back on, all the work and the answer will be posted. So in finishing out this problem, we see that we chose the second equation because it has a larger K. We set up our Rice table. We solved for X. X turned out to be the OH concentration, not the H concentration, the OH concentration. Negative log gave us a POH of 3.90. Therefore, the pH of this one was 10.10. Ta-da! Fini, or fin. Well, Fini is a different language, but it's just fin, because it's a movie. Let me write that. Fin.